Welcome to Security Architecture Podcast, where we help cybersecurity professionals to stay ahead of the curve and ensure they are successful in their cybersecurity journey.
Hi, I'm Evgeny.
Hi, I'm Dimitri.
We have here Kieran from Garantir. Can you please tell us about you and the company?
Hi, it's a pleasure to be here. I'm Kieran Miller. I'm the chief architect at Garantir, where we focus on cybersecurity solution problems. And one of the core focus points of us is we deal with the CICD pipeline and securing the signing process within the CICD pipeline. In particular, we want to ensure that what we're signing matches what comes from the source code repository, and to do that in a scalable manner.
Kieran, in your opinion, where I would be using Garantir's product in CICD pipeline?
Sure. So our product GaraSign is, like I said, it deals with the signing process. So it definitely happens after the build occurs. So after we compile the source into binary. Now, after that, it's really dependent on the customer's environment. So in some cases, you need to sign the code before you start integration testing because some platforms just require that. In some cases, you do it after the integration testing. But at some point after the build occurs, our customers are signing their code. And that's where our product GaraSign gets invoked.
Right. Would you like to share some more information about the architecture of your solution?
So here's the architecture of our product. So at the bottom left-hand path, this would be where the build server is trying to sign code in the CI/CD pipeline. Now, a core component of the way our solution works is that the keys remain non-exportable in usually an HSM, a hardware security module, or some type of KMS, a key management system. These could be cloud provided, or this could be on-premise. It doesn't really matter. But the build server who wants to sign the code here at the bottom left will go ahead and talk to the signing server right here, typically via a load balancer, and that will offload the request to the HSM for signing. Now, that's the main part of GaraSign that people think about. But of course, there's more to it. There's an administrative server for administrative capabilities, notifications that can be sent via Slack or email, Microsoft Teams, a database for persistent records for audit history, et cetera. But the core focus point is this bottom left path.
Is the HSM something you guys develop or OEM from somebody?
No, so the HSM, typically our customers either already have one, so that these are commonly bought from companies like Thales and Trust, FutureX, or they're getting one from their cloud provider. So AWS provides the cloud HSM and KMS, Azure, and Google also have similar offerings. So we support any of those. We in fact support multiple different types of HSM simultaneously. So we don't provide the HSM. We're providing the infrastructure to use the HSM in a secure and efficient manner. We like to say that the keys and the HSM is the castle, and we're providing the moat, the drawbridge, the guards, and everything to make it into a fully functional city.
In this makes sense that majority of the time you guys will be in the cloud, or there's on-prem version as well?
So we deploy both. So for our customers, they typically have a strong on-premise environment, but they also are migrating to the cloud. So we actually typically will do a hybrid for them where they have HSMs that are on-premise, they have some that are in the cloud. Now for code signing, which is one of the main use case we're talking about here today, those are really crown jewels to a company, because if you compromise the code signing keys, you can do some pretty catastrophic things, as we've recently seen. So some of those companies like to keep those HSMs on premise, but we can still deploy our infrastructure in the cloud and talk back to the HSM on premise.
So the signing server cluster will be running on-prem of the customer.
In some cases, in other cases that it's running in the cloud. We do both. And in some cases, we're actually hybriding between the two. So we use the cloud for when they're bursting. So some of our customers are doing insanely high volumes of signatures per year. And so in that case, they are bursting in the cloud when they have peak volume, and then they're scaling down to just being on premise when it's low volume time.
In this case, you mentioned code signing. Will this be developers? Will this be DevOps? Will it be security analysts? Who will be the main user of the product?
So most of the consumption, the bottom left, that signing client, 90+% of our customers have that coming from their CI/CD pipeline. So the build server itself, so the agent running Jenkins or TeamCity or something like that, is the client. So it's usually an automated system. Now, in some cases, customers also like to have very formal production release cycles. And in that case, it's actually like a change release team that's manually running a tool like Sign Tool or Jar Signer to sign the code. But effectively, whether it's a human or it's an automated system, they're still doing the same thing. They're running a signing tool to sign some binaries or source code and get the signed result as the byproduct.
Application security solutions aiming to identify and prevent security deficiencies in the SDLC process. And they try to do it very early. How your solution contributes to this, and if you can maybe share with us how it integrates into the CI/CD.
So what I have on my screen here is a kind of summary version of the CI/CD pipeline, right? So at the top left, we have the developer who commits code changes to the source code repository. Those source changes go to the build server, which then compiles it, and eventually it's signed, and then unit and integration testing occurs. I will caveat that sometimes you do unit testing first, then sign the code. Sometimes you do integration testing, then sign the code. So that order at the very end can vary, but it's roughly that idea. Developer commits code, compile it, build it, sign it, move on. And so what we found is that one of the more advanced attacks that's going on is that malicious parties are trying to use legitimate code signing keys from companies to sign their malware. Now, the reason they want to do that is so that they can masquerade their malware as legitimate software and they can bypass antivirus and spread it more easily. Now, the way that they do that, there's a couple of ways that they can actually go in there and compromise the keys. Let's see. There we go. So the first is they can compromise the signing key itself, right? So they can steal the key. And if they can do that, they can actually perform offline signing. This is arguably the worst case scenario because they can just sign at will in their, the convenience of their own home, and you would be none the wiser. The second way that they can do it is they can compromise the build server. Now in this case, they don't have the key themselves, but they have access to a system that is allowed to use the key. And therefore, as long as they have access to the build server, they can sign malware. And this, of course, happened in the recent case of the SolarWinds attack. The next way is if you can't compromise the build server, you can compromise the source code repository. So this is where you're actually injecting your malware into the source code repository. Now, this is not a great solution for the attackers because it becomes very visible. So assuming you're using a modern source code repository, that history of that malware being injected is going to be there. And so the chances of it getting detected is very high. There is a nice pro for them in that as long as it's not detected, the malware will remain and persist. But assuming that the company is doing any decent source kind of code review or something, it'll be caught. And then the last is an insider threat. Now, the insider threat is really just a mechanism to do one of the other three attacks. Right? So either you're going to get the insider threat to inject it in the source code repository, you're going to get the insider threat to effectively either compromise the build server or just go to the build server and run a signing, or you're going to try to get the insider threat to steal the code signing key. So it's just really a special case of the other three. And so our system was designed to protect this. And so effectively what we're doing, we were just talking about the HSM. So the first case where we want to protect the key from being stolen, the HSMs, the hardware security modules, they already do that for you. That's not even, we don't sell those, we don't deal with that. We just integrate with them. So getting your key in some form of hardware protection is the first step. So that way the keys are non-exportable. You can only use them by talking. You can only feed information to the HSM, which will then perform the cryptographic operation, in this case signing, and it'll feed out the signature. So even you yourself, it's your key, you don't even get your own key bytes. Then the next thing, this is where things start to get more interesting, the build server, right? So if the build server has access to use the keys, how are you going to stop someone who compromises the build server from signing something that they shouldn't be signing? And this is where things get a little more advanced. So you actually need to put a proxy server in front of the HSM, which is what Garantir is. And you have to configure the proxy server to talk to the source code repository and say, hey, I want to make sure that the hash that I'm signing is a byte for byte match for what comes from the source code repository. And that's high level what we're doing here. Now, it gets more nuanced than that when you want to add in performance and scalability. But the general idea is making the signing server that proxies the HSM reach out to the source code repository, perform a deterministic build or a reproducible build, and then compare byte for byte that the hash that you're signing is a one-for-one match for the hash that was requested to sign. I'm going to pause there and see if there's any questions or commentary to go from there, because we can work backwards and then talk about how we protect the source code repository too. But that is arguably the most interesting thing as it relates to code signing.
How are you making the connection between what is in the source code and what was actually built?
This right here is just another diagram of what we were looking at before, but we took the developer out of the picture just to simplify it. So now at the top left, we have the source code repository. Then we have the build server. And then now you'll see at the bottom, we have a cryptographic service. So in our case, that's our product, Garantir. But in general, it's something that's proxying the HSM. And so what's happening, now we have to back up for a second and actually talk about what is hash-based signing. So there's an important thing that happens in a digital signature. It's made up of two components. First, you hash the data that you want to sign, and then you apply the private key. And so one naive approach to signing when the keys are in the HSM is to upload the code you want to sign to a server, sign it, and then download the result. The problem with that approach is that it eats up a lot of bandwidth and it's incredibly slow, especially when you have developers all over the world, and most companies keep their keys in a couple restricted zones. So for example, if you're a Western company, you probably keep it in the United States, maybe parts of Europe, but you may still have developers in Asia and South America, and that gets very slow. Additionally, it is a security issue to upload rogue binaries to a server that has access to your keys. So it's not a good practice. So what people do, a more advanced way, is to actually break down the digital signature into the two steps. And the first is computing the hash, and then the second is applying the private key. So a nice byproduct of the hash is that it doesn't matter the size of the file you're signing, the hash is always fixed in length. So you could be signing a 2 gigabyte file, the hash is going to be roughly 256 bits. And so when you are hashing first and then uploading to the server, you can go blazing fast regardless of the file size. So when we're looking here, you see these thumbprints there. Those thumbprints are indicative of the hashes. So what we want to know as the cryptographic service is the hash that I'm receiving to sign, does it match the hash that comes from the source code repository? That's what needs to be answered, right? So when the build server sends the request, we can also tag other information about the request. For example, the revision that it comes from the source code repository. And the cryptographic service actually has to have it has to imitate what's going on with the build server. So it has to imitate the build process. So it's going to say, okay, you are claiming that this hash matches what comes from source revision number 123, whatever, some source revision number from the source code repository. The cryptographic service is now going to say, okay, I'm going to go out to the source code repository. I'm going to pull revision 123. I'm going to do the exact same build process as you. And this is where reproducible builds are very important. So it has to, given any two sets of, or any same set of source code, when you do the build process, it has to produce the same byte for byte match on the build process. This is what reproducible builds are.
And with different compiler, even different flags to the compiler, you will get different hashes in the output.
Yeah, so you have to do the exact same flags. So what we're doing is most of our customers have their build environments virtualized. So they say, okay, I'm ready to run this in a container or whatever. We say, great, give us that same exact image on that, and we put a thin agent on there which does the verification part, and it runs the exact same thing using the exact same source code, and it better produce the exact same output. So the flags and everything are exact one-for-one match.
I'm wondering, in majority of the products that need some kind of access to the people code, to people laptops to actually check what's happening, you guys work differently. So what kind of access do you need and where?
So the cryptographic service here, when you're using this feature, it needs read access to the source code repository, and it needs access to the HSM, the hardware security module, which has the keys. And so when it receives that request, that's when it says, okay, I need read access to the source code repo, and it also needs the ability to do the exact same build. Now, I'm actually oversimplifying things here. What it actually looks like is here's our architecture. The signing server is not the one that's actually doing the verification. It then calls on to this node over here, the build verifier, and it sends a message over saying, hey, build verifier who handles this particular project, I want you to independently verify this information. I received a request for this project with this revision number. Please go ahead, run the build process and tell me the hash that you get. And then it reports that hash back to the signing server, which then says, does that match the hash that I received as part of the request to sign?
So you don't actually know the code yourself. You're just checking the signing.
Well, so the build verifier will get the code and it'll build it. We don't execute the code. All we do is we compile it, produce it, and then say, okay, we're going to run a signing tool, compute the hash, and say, does this match exactly? Because if it doesn't match, then it didn't come from the source code repository, or there's a problem with it. There's a misconfiguration between the two build environments.
Do you save the code anywhere?
Optionally, yeah. So if you optionally want to then upload the what we compiled and built, you can. It's an optional add-on. So if you want to push it to like Artifactory or something, you can, but it's not a requirement. We definitely save the hash that was produced, but we don't necessarily save the binaries because, so we do some other fancier things beyond that. So this is where we can get into parallel processing of like doing static analysis and all that. And we do that to actually bring down the overall build time. But that's a secondary thing. The first thing that we're really doing here is we're really trying to answer the question, is what's being signed, does it come from the source code repository? Or is someone trying, because essentially the problem all comes from this. Source code gets converted to binary and the hashes change. And we need to know, what is this hash that you're claiming comes from the binary? Does it match what comes from the source? And that's where the big disconnect is. That's where the attackers are saying, well, I can just put my own binaries here, claim it came from the source code repository and move on with my life. And now I'm really signing something malicious and it's really hard to tell, is this legitimate? So we want to know, does this match what comes from the source code repo? And we're treating the source code repo as a source of truth.
How secure is the signing server?
The signing, I mean, we obviously think it's pretty secure, but it depends on how you deploy it. I mean, there's a lot, so we don't load anything else on there. There's we go through pen testing with NCC group and all that good stuff. So we do that regularly. That it goes through a secure boot process, all that stuff. We can even use secure enclaves for parts of it. But at the end of the day, we do have some guarantees that even if the signing server got compromised, you definitely won't get the keys out of the HSM because the HSM has its own physical protection. And then we have some other auditing that goes on, that the nodes independently audit each other. They do remote attestation to each other to constantly keep each other in check. There's a lot of internal things we have and for anyone who's interested in this stuff, we have a threat model which goes over all the threats and all the preventative and detective controls that we have in place for this kind of stuff.
The signing server mimicking the build, your build server, and what kind of languages do you support, or like what it can build?
Yeah, good question. So technically, when I first said it, I did say that the signing server is doing the verification. I was just keeping it simple to, since we're just introducing the topic. Technically, it's the build verifier that you see on the screen all the way to the right. That's actually what's doing the verification. The signing server doesn't even know how to verify. All it knows how to do is to route a message over the message broker over here and say, hey, build verifier, I need you to verify this. Now, the nice part about that is our build verifier is mostly just the customer's code. It's the customer's build environment. And we put a thin client on there that knows how to receive requests from the message broker. And then everything is offloaded to the customer's environment. So we don't really care what language it's in. We don't care if you have a build process set up, we just mimic exactly that. And so the last mile is just a call back into your build process to say, please build this, push the final artifact out here, and then we'll run the signing command and pull the hash and send it back to the signing server, which will then say, is that hash match or does it not?
So let me see if I understood it properly. So the build verifier is actually some type of agent that's running on my build server. And what it does, in my understanding, it looks at the source files, hashes, just a millisecond before they've been built.
Kind of. So it's not the build server that's actually requesting to be signed. It's a copy of a build environment that runs separately from the client. we can't ask the client to verify what it just sent to us. That would be kind of not secure. So it's a duplicate copy. So let's imagine you have two build servers. One of them is dedicated to us on the server side, and one of them is the actual build server that runs in your CI/CD pipeline. We are giving it to the duplicate copy that has no network relationship or anything to the actual one in the CI/CD pipeline, and we're saying, please verify what this build server has claimed is the hash.
Okay, so I have to set up two similar build servers in my environment.
Yes.
One of them goes to you, right? And that's where you're installing your solution. And one of them just connected to my CI/CD pipeline and continuously builds. This build actually executed on both of the build servers, and then you're comparing between them to make sure that nothing has changed.
Yeah, it's nothing more than independent verification and validation, right? It's just another node just doing the exact same. It's like, Dimitri, if I told you to do the exact same thing and say, hey, did you get the same result? All right, cool. And it's just an audit test. Now, we're not a SaaS offering. At least this part's not a SaaS offering. So all of this is running in the customer's environment. They already have their build environment. They already have it virtualized. They already have containers to run this stuff. We're just saying, give us access to one of those containers, and we configure that as the build verifier.
Okay.
And now keep in mind, now when you actually get into deployments, you're going to have build systems that are running on different operating systems. They're running different code bases and all that. So we support multiple different build verifiers running different environments, and they'll, based on the project that the client is claiming that they're compiling from, it'll route to the appropriate build verifier to do the verification. Now, the interesting thing comes in when you start talking about performance, because you may have noticed in the beginning, I talked about client-side hashing as a way to improve performance when the keys are locked away. But everything I just said right now about doing another build, another hash validation, sounds really slow, and it is. And so at first, so if you think about it, there's actually two ways to do the verification, and we support both of these. One is what we call pre-sign validation. That means before I allow whatever the client is requesting to be signed to get signed, we do the validation then. And then we also do post-sign validation, which means the signing server immediately signs whatever it receives, and then it'll start the build verification process. Now, this is less secure, but it goes blazing fast. And so it's really good for the CI/CD pipeline for 90% of the case where you're signing using your non-production key. And then when you go to sign with your production key, that's where you want to use pre-sign validation, which is slower, but assuming you're releasing, I don't know, quarterly or something like that, it's not that bad.
Because you specifically work with pipelines, I'm guessing you need to support many different pipelines. Can you elaborate more? Is there specific pipelines, CI/CD solutions you're working with?
Sure. Yeah. So the way that we do the integration is we're really integrating at the time that the signature, the signing occurs, right? And normally, and that is triggered by the build server. And so the way we integrate is all of these various tools and frameworks, they have client integrations. So if I can click here, we support a wide number of client integrations so that you can use the native signing tools that you would normally use, but it'll work in this environment where the keys are in the HSM behind the signing server. So for example, if you're running Microsoft Sign Tool, it uses something called a KSP. Back in the day, it used to be called a CSP. Now it's called a KSP. We provide a KSP so that you can hook into it and continue to just run Sign Tool the way you do today. Similarly, for Java, we have a JCE provider. For Mac, we have a CTK, a crypto token kit, etc. And so at the end of the day, the way we're hooking and supporting all these environments, these different build servers, is by providing these client integrations. Without these client integrations, to be honest, none of this would matter because it wouldn't integrate with the tools you use today. And so you would effectively be breaking the build process on people. So we can actually go into existing build processes that they're already signing using keys that are locally stored in software. And we can move to an environment where the keys are in the HSM and it's doing all the validation without changing the build script at all.
Thank you. We want to move to open discussion.
Mm-hmm.
And maybe you have questions to ask. I have a question to you.
Sure.
So we spend a lot of time to talk about how we can secure the code and prevent supply chain attacks and many other things. In my practice, by talking with many different customers also afraid that somebody may take the code and steal it or give it to somebody else. Do you guys play in this role as well?
We do a little bit in the obfuscation. So we do have customers who say, hey, I like that my code is signed. We have another practice that we don't actually talk about as much as we should called software monetization. And so it deals with a couple of things. One, they want to make sure that people who, these enterprises that produce code, they want to make sure it's only being used by people who have paid to use their code. And then the second thing is they want to make sure people aren't decompiling and reverse engineering their stuff. So for the first one, we do have some licensing capabilities, which are cryptographically bound. And so you can actually enforce licenses on your software so that the software kind of stops working at predefined times, or if they haven't paid, that kind of thing. And then the second thing for the decompiling, it's standard obfuscation stuff. It's nothing above and beyond, but it's doing the obfuscation to make it more difficult for people to reverse. Now with the more prevalence of secure enclaves, we are moving into that direction to say we can move a core part of your code processing into a secure enclave, like AWS has the Nitro enclave, Intel has the SGX chip, and you can actually move the parts that you don't even want people to see into the secure enclave and move that core part. There's a little bit of a performance loss as a result of doing it, but if you are concerned about people stealing your intellectual property, or you want better enforcement of the software licensing, that's a great way to do it.
These methods of obfuscating, are they available for various languages and the frameworks?
Yeah, most of them have them. To be honest, it's not a big part of our practice, and we're not actually using anything like new above and beyond. We're using standard open source available and some commercially off the shelf available. That one, we're more helping customers do it, and we're helping them do the obfuscation before they do the signature. Because if you do the obfuscation after the signature, you're going to invalidate the signature. So we more help them integrate that into their pipeline, but we're not writing any new obfuscation techniques or anything like that. And we also help them, balance that line between obfuscation and performance degradation.
Kieran, thank you very much. It was our pleasure to have you here on the podcast.
Yeah, my pleasure. I had a great time. Enjoyed talking to you guys about this, and hope to be back here soon.
Excellent. Thank you, Kieran.
Thank you.
Please remember to subscribe to our podcast and join us for our next episode.